Another important aspect is, specifying the message format. For example, here we specify, the message format for, let's see, for the RPC bind. So this is a little bit like the struct in C. And this, the keyword skip is really saying that you do not need to save any state for those fields. When you're parsing them, you only need to remember you're parsing that field, but you don't need to save the content of that field. So this is trying to minimize the state maintenance issue. In the handler, over here, in the when you first, so this is the handler when you first receive a RPC bind message, and we're looking for the UUID here, and this UUID represents the RPC call that has that contains the that's vulnerable, that has a buffer overrun in it. Then later on, if that RPC bind request is trying to invoke that RPC call, then we continue maintaining the session context for that session. And then when you receive the RPC request, you check for the buffer size. If the buffer size exceeds this legal limit of 1023, that means that you are being exploited. So then we tear down the communication session and return the final state for that session. So that's pretty much how the next level of detail of our shield design. So next time, I'd like to give you analysis on this design. So first, on the scalability. So the scalability here is really how can we scale with the number of vulnerabilities. First of all, the number of shield does not grow indefinitely. We envision that after you apply shield, after you apply your patches, then the corresponding shield can be removed. Even if you don't remove that, the shield doesn't really, the scalability is still pretty good for shield because shield does application level filtering. You only filter the vulnerable applications. So if you have n vulnerabilities, vulnerabilities in n applications, then that's pretty much equivalent to one vulnerability for each application. I'm sorry. So you have n applications, one vulnerability for each application, and this is equivalent to the overhead of one shield, basically, because of this parallelism at the application level. So then the next concern may be, okay, how about in applications like Internet Explorer or web server, there can be multiple vulnerabilities in that single application. This is also not very significant according to our study on the security bulletin of the Security Bulletin Board from 2003. Basically, we find that there's no more than 3 wormable vulnerabilities seen in any single application in 2003 for the wormable ones. So also, you may worry about application throughput. Okay, here I'm giving you maybe the worst case scenario. The worst case scenario is the application throughput is at worst about halved. But actually, this would be very low impact for the customer machines. But for the server machines, you may be worried about that. But our actual evaluation shows that the impact on the application throughput is actually very small. So some analysis about the false positives. Because shield is vulnerability driven, so basically we have a near zero false positive rate by nature. However, there could be 2 sources of false positives. There could be a misunderstanding of the protocol or payload specification, as we talked about before, and this can be debugged. This can only be debugged by trace-based testing or test suite-based testing. There's also another source of maybe somewhat more contrived example of when false positives can occur. That would be for some network event, there may be a different treatment of that event based on some runtime condition, maybe based on local configuration, or maybe based on some application logic. In one scenario, it's not an exploitation. In some other scenario, it is. I think this kind of false positives will be, we should actually block those kind of traffic just to be safe. Okay, so now I'd like to tell you more about our prototype implementation. The shield prototype implementation is based on the layer service provider from Windows. What this LSP does is really intercepts the transport layer protocol, basically intercepting the send calls, receive calls open and close socket calls. And then the shield logic is inserted in those interceptions to do deeper inspection. This is about like a 10,000 line of C++ code. Some of our shielding experience is quite positive. We have working shield for a number of vulnerabilities. We have, the shields, working shields behind, for the vulnerabilities behind Blaster, Slammer, and Code Red, and we have more of those these days. We have done detailed study over 15 vulnerabilities and 7 protocols, and we have more of those protocols as well. This talk is slightly out of date. We also have done some throughput evaluation. So basically the shields for Blaster, Slammer, and Code Red, they have very little state. We need to maintain very little state for those vulnerabilities. Typically, it's less than 32 bytes. And also, they have very small number of states. So they incur actually very little overhead for the end-host system. So because of that, we have designed a more stressful shielding scenario. So we assume there's a server sending data to clients as fast as possible in an RPC-like fashion, in an RPC-like session over the Ethernet switch. And each session requires, each session will require 1 kilobyte of partial payload to be saved. So that will be part of the session state. So it's much more stressful than the working shields that we have, which is only 32 bytes or less. And we put an outgoing shield on the server, and what we want to see the impact on the server throughput. We used a 3.606 gigahertz CPU and 1 gigabyte of RAM for both client and server, and they're all running Windows XP. And we first use a 100 megabit per second Ethernet switch for the experiment. We can see that here, the network, the Ethernet switch is the bottleneck, and the CPU is very fast, so we can achieve pretty much the maximum bandwidth here, maximum throughput here for all clients. However, we can see some variations in the CPU usages. Like when there are less than 50 clients, the LSP, so we sort of divided up the cost and see how much LSP costs and how much shield adds to that cost. So LSP incurs rather large overhead, is about 11 to 28% of overhead, and shield only adds a little less than 3% more overhead. So after inspecting the LSP code, we realized that overhead of LSP is actually not inherent. There's some heavy copying of the socket context that causes that overhead. So that overhead can potentially be removed by very much. We also conduct the same experiment over a 1 gigabit per second switch, and looking at the throughput for the server. Here, obviously, the CPU is not fast enough to keep up with the network bandwidth here. So we can see a degradation of the throughput as the number of sessions increase. So LSP degrades the throughput by about 12%, and shield degrades by 11% more. Okay. So now I'd like to talk about some of the related work to shield. So many studies have shown that the fast spreading and wide spreading nature of the worms. People have done a lot of extensive research in the compile time static checking, basically doing static checks for the buff overruns at the source code level. Basically, in that piece of research there's a trade-off of false negatives and false positives. There are also a number of mitigation techniques, such as stack guard and non-executable stack or heap. But these techniques can also be circumvented by the attackers with different with new attack techniques. And also, these techniques often lead to a service denial of service attack, basically causing the system to crash. There's also, for the exploit-driven firewalls, there are new